Hello, welcome back. Today we will discuss evaluation of rules. So far we talked about how to generate item sets that we can then use to generate rules. But once the rules are generated, we need to decide if those rules are valid or not necessarily it is valid, but it makes sense or it's useful. So we need to have some way to actually evaluate the quality of the rules that are generated, because we will be generating lots of rules from even a limited number. So we need to decide on certain ones and act on those. So for those rules, we need to somehow know or figure out how it is interesting. So we are more interested in rules that are interesting. So interestingness measures can also be used to prune, rank the patterns and eliminate some of those unnecessary rules. In the original formulation we talked about support and confidence, but there will also be other measures that we can introduce in this section. So how do we compute interestingness measure being interesting? So given x implies y or xy together, information needed to compute interestingness through contingency table. So that is a contingency table. We have, it's a pair, pay attention to that. We have x, y, and we have also negations like x naught and y naught. So in that table we have f11. That means that support of x and support of y together. If it is x and y naught, then it is f10. So, and then we have totals, f1 plus, f0 plus, f plus 1, f plus 0. So those are the row totals and column totals. So this is a contingency table that then we can use in our formulas to actually come up with some of the measures that we will discuss in the following slides. We talked about already support, confidence, and Gini and entropy, but those also can use these tables. So what about confidence? We have confidence, but will that not be sufficient? And I'll give you an example case where this may have an issue. So we have customers and those are transactions. It is tea, coffee. Customer 1 got tea, did not have tea but have coffee. Customer 2 have tea but no coffee. So you can look these as transactions. Customer 3 has both tea and coffee. And we can from that table produce a contingency table cross of tea and coffee, and out of so many transactions, let's say we end up tea and coffee together 15 times. When a customer got tea but not coffee, that's only 5 times. So let's assume that out of 100 transactions we can actually split those into that table. So from that we can look at confidence and calculate it. So this is like probability of tea given coffee. It's a pair, so we can actually calculate it such that. So out of 20 tea, so you can look at this row here on the top. We have 20 total. So out of 20, we have 15 times we got coffee. So that is 0.75, which seems to be high, right? So normally 50% of confidence is meaningful. So who drink tea that are more likely to drink coffee than not drink coffee. So this might be a reasonable rule based on that. But I'll show you the case. So if we only look at people, out of 100 transactions, we have 90 people that got coffee already. So if you think about it, 90% of the people already, or 90 50% of those transactions are already including coffee. So it's already likely that it will be there. So when I find a 15 or 75%, for instance, confidence, whereas just coffee itself is 90%, that makes it kind of interesting. So in reality, that means that actually having tea reduces the probability that the person will have coffee. Not increase, but in fact reduces. Even though just looking at confidence, you may conclude that. But if you have tea that is 8 tea nut, so this has a bit missed that I need to probably fix it here. So that this should have been tea nut right there. So if we have people who didn't got tea, so this is that's 80%, and how many of them got coffee? That is 75. So that is even higher. So it means that people who did not got tea are more likely to get coffee than the otherwise. So this might be actually good, interesting rule that we can probably follow. So what kind of rules do we really want? So we want confidence should be sufficiently high. So that is also desired to ensure that people who buy X will more likely to buy Y than not buy Y. So, but that itself may not be enough, right? Confidence of X implies Y has to be greater than the support of Y itself. So like if it is, let's say, coffee 90%, if I have a confidence that's higher than the support, then it can be interesting. Otherwise, rule will be misleading because having item X actually reduces the chance of having item Y in the same transaction, like the one we just show you here. So is there any measure that captures this constraint? And we will present some. So we need to talk about first statistical independence. So when we actually say that we have to consider two cases: when we are statistically dependent and when we also have statistical independence. So if it is statistically independent, confidence of xy is equals to support of y. And if you remember the formula for confidence, so it is probability of y over x, right? So if you look at is equivalent to probability of y given x equals to probability of y. So in terms of statistical independence, we can actually come up with this relationship. If they are also independent, joint probability is going to be the multiplication of these two. If they are independent, like what's the probability of getting two heads? They are independent. It's random completely, so you multiply. So it is like that. So this is a joint probability, and you have to multiply those two. So if probability of xy is greater than individual probability multiplications, then they are positively correlated. If it is less, then they are negatively correlated. Right? So this is something to keep in mind. So this will also show us some correlation. I might need to actually show why this is the case, because support of y means that y out of all transactions, right? And confidence x implies y means that. So you have to given x, so that is going to be on the at the bottom of that equation. So that is the number of x, but then you have to look how many times you see both x and y. So that is confidence. So that is also why we are having the same equation. And I will pause for a moment and I will actually bring that equation to show you that. Just a second. I just added confidence definition measures how often items in Y appear in transactions that contain X. So if you remember, we will have X and Y jointly happening together divided by the probability of X. So if you look at it, this is how you can restate in statistical terms, assuming statistical independence. It is given X, Y and X happening together, meaning that it is probability of X times probability of Y. So they are happening together divided by probability of X. So if you simplify these two terms, you will be left with probability of Y. And probability of Y is actually equivalent to support of Y. So out of all transactions, how many times you see Y? So that is how it is related. So when we have this relationship, probability of X times probability of Y is equal to probability of XY as a joint distribution, like if this is equals, then we are assuming statistical independence. But if they are correlated, then they can be either positively correlated or negatively correlated. So that is two possibilities. And if it is positively correlated, then it should be greater. If it is less, then it is negatively correlated. So keep this in mind. So what is lift? When we use statistical independence, we have an equivalent relationship, but in the case of statistical dependence, if they are not independent, like they are correlated, like here, then I can actually come up with two or actually these are four terms, they are different terms. I can either use lift, interest, PS, or gamma phi coefficient. So lift is used for rules while interest is used for item sets. So this is something to keep in mind. We are looking for interest in the item sets, but we will be using lift to evaluate rules. And lift is given with this formula. It is defined as this, and interest is given in this formula. There is also PS, which is given with this formula, and there's coefficient. I think it's phi coefficient, and this is given with this formula. So you don't need to memorize these formulas, but we have definitely different measures that we will be actually evaluating either the item sets or the rules, especially in rule generation phase. So when we have statistical independence, we have this equivalent relationship. So if these were equivalent, then probability of Y given X is going to be rewritten as probability of Y times probability of X divided by probability of X. Then we have probability of Y as well here, so this will become 1. So if it is independent, then the lift is 1. So this is something to keep in mind. So let's look at example here with lift and interest. We have an association rule. Tea implies coffee, or you can also reword it as if I got tea, then I will likely get coffee, for instance, if this is a rule. And this is our contingency table, again the same table. And if we calculate confidence, we got 0.75, but we also stated that just the probability of coffee is 0.9. So you can look at lift here, and lift is calculated using this formula here, and if you put in numbers there, then probability of y given x, this is, you can maybe say coffee is x and tea is y, or vice versa. So 0.75 divided by 0.9, so this is likely coffee, and this is likely related to, let's look at formula here, this is probability of y and this is probability of y given x. So here what it says us is, this is probability of coffee, right, and this is probability of coffee tea. So you divide confidence with this probability basically in the lift, and what you got here is 0.833, and if you remember from here, it is negatively correlated, so it's not really a positive correlation. So we can therefore say that it really does not imply that, it actually implies the other one, like having not tea means coffee more likely. So if we have a situation like this, we have 10, 0, 0, 90, and we have 90, 0, 0, 9, 10. And if we calculate lift for this table, then we have 10, and if we calculate lift for this table, then we have 1.11. So as you see, if it is almost symmetric, like here almost flipped, but if you plug in these numbers, this is what you will get. So it is very different. So if it was statistically independent, then we would have lift as 1. So these are definitely not statistically independent, and they are correlated, and we have very different lift numbers for whatever x or y represents. We have very different numbers depending on how we actually rearrange the numbers. So it can vary a lot, as you see here. So there are a lot of other measures in the literature. We talked about phi coefficient, and there is kappa, there is Gini index, which we already know, but then there's a lot of others. You don't need to know all of these, but you just need to know there are a lot of others, and each have different advantages and disadvantages, and it is applied to different problems. So here we have these indexes or measures we just talked about, rankings of the contingency tables, and these are examples. We have so many, let's say 10 examples here, and this is our contingency table for these 10 examples. So we have E1, these are, remember from that for entity we have a pairwise comparisons, and these are the numbers we got. Basically these are the counts, and if you plug, just using this table, you plug these numbers in, you will get very different ranking. And which is interesting is, like for instance, if you take E10, example 10, here this is your example right there, and these are the support or count values. So while in one index it can be it may get a mark of 10, and the other one it may get 1. So this is showing you how it can change a lot. So even in one example, different indices may indicate that maybe this is a good thing or a bad thing, but it will actually be flipping a lot. It can change a lot. But here, if you look at E8, numbers are pretty high for all, but E8, this is maybe more balanced. and we have a little bit more consistent reading on these numbers. But here we have not so much of a balance, and we have huge changes. We have as low as 1, we have as high as 10, so that varies a lot. So this is something to keep in mind. So we have different situations, like when we have this contingency table, and these are values, like how many times, maybe p times they together appear, q, r, s. These are again contingency numbers, and if we revert it, we have a and a naught, b and b naught, and we put in the same numbers. Just flip it as you can, property under variable permutation. So we have changed, and we look at now the numbers back again, these numbers. So if they don't change after I made that switch, like flipping, if whatever measure I have, AB is equal to MB, M again measure BA, then I may call this symmetric. So if you look at it, support, leaf, collective, strength, cosine, Jacquard, and these are symmetric. And we also have asymmetric measures like confidence, conviction, Laplace, J measures. So these measures can be property under variable permutation. Property under variable permutation. So it may vary, right? As I change, it may be, depending on symmetric or asymmetric, it can actually have a different number if it changed under variable permutation. So under row and column scaling, will it change? So that's another one. So we have this contingency table, and somehow I decided to multiply these females by 2x and males by 10x, and definitely I will have very different numbers. So underlying association should be independent of the relative number of male or female students in the samples. So this is desired. We want it to be invariant under scaling, so we don't want it change. But you can also look which will change and which will not, and some may not be affected as others if you, for instance, plug in the numbers in these formulas. So this is another property of these rule evaluation measures. Do they change by scaling, or do they change when you switch sides? Sometimes you may want that, and sometimes you may not want that. If you invert, I have AB, this is 1, 0, 0, 0, and 1, and everything is 0, 0, 0, 1, somewhere in the middle, then bunch of zeros. But what is more important here is where those ones and zeros are not so much important, but it is if you have C and D, which is completely opposite. Like when there's 1, there's 0, and when there's 0, there's 1 in C and D. And E is more like C again. So what you care here is, do they, if I invert, do the results change? So some properties do not and some do. Again, you can use counting and look at it. So if we have phi coefficient, it's analogous to correlation coefficient for continuous variables, and we have these contingency tables, 60, 10, 10, 20. So we have out of 100, this is how it is split up, and this is almost this 60, 10. This time it is 10, 60 in the nuts, right? So it is inverted, and we have the same phi number for this table as well as this table. So in that case, because this is invariant, under the inversion operation, we have a different property. Property under null addition, what does it mean to add null? So everything stays the same in the table, and somehow you are adding more irrelevant things to this size, or you are changing the sample size, for instance, but none of those new samples are either related to A or B. So you are adding into A naught and B naught. So this is property under null addition. So support, cosine, Jacquard are not going to be affected because it only counts things that are related with it. But others like Gini, mutual information, odds ratio, correlation will be affected. So depending on your requirements, this is something to consider. Here a summary of different measures with different properties in a table. Like, for instance, inversion, is it sensitive or not? Null addition, no. It supports or not supports, I believe. If you scale, it will be affected. Inversion, it won't be affected. I believe it means invariant. Like if you take one, for instance, here, invariant support for null addition. So yes, support, do I have it? Support is invariant under null addition, right? Null addition. So that is null addition, it is invariant. It is not sensitive. So this is how you can actually look sensitivity of different measures to different properties. So we have also Simpson's paradox. Observed relationships in a data may be influenced by the presence of other confounding factors, which we have hidden variables, and that can actually change the outcome. Hidden variables may cause the observed relationship to disappear or reverse its direction. I will give it an example in the next slide. So proper stratification is needed to avoid generating spurious patterns. So proper leveling or splitting is needed, adding new layers to account for those to avoid generating false patterns. So let's look at Simpson's paradox here. We have HDTV buy versus we have exercise mission buy. You will buy or not buy, right? Yes is yes, you buy, no you don't. So if you look at this table, again this is a contingency table. If you buy HDTV, you will buy also exercise machine, more likely, right, than not buy it. So, and if you don't buy HDTV, then you buy exercise machine, no. So looking at this, given that you buy HDTV, you will buy exercise machine, yes, is 55%. And given that you don't buy HDTV, and you telling that you will buy an exercise machine, like 54 times you will say yes, but 66 times you will say no. In the case of when you buy it, it is more likely, right? You will say more yes than no. In the case no, then you will say more no than yes. So it is almost 55 to 45% confidence. So these are confidence numbers. So from there you can say that if you buy HDTV, you are more likely to buy exercise machine. So this might be okay, it makes sense from this table, but I will show you if you deep dive and look into underlying data, and we have maybe additional data. So here we can assume that HDTV is driving people to buy exercise machines. That may be a conclusion, but if you look into more detail, and if you split the group into college students and working adults, so this is adding a third dimension almost. But I only look at two at a time if you pay attention before. So if you look at this, college students, HDTV yes, exercise machine yes, 10% of the time. So if you look at confidence again for HDTV no, exercise machine yes. So I'm splitting into college and working adults. If you pay attention, I'm doing the same thing. So it is 11%, not so much difference, slightly in fact almost negative. So what it says here, that if you buy HDTV and a college student, you will not buy exercise machine, as it is more likely, right? So if you say no, you buying an exercise machine, yes, is more likely, maybe 1% more likely, but it's not, again, this number is not too much different, but I'm telling you that it is looking like as if it is almost working otherwise. And if you look at working adults, if you don't buy HDTV, what percent of the time you will buy exercise machine? That is 58% of the time. If you buy HDTV, and what percent of the time you'll buy exercise machine? That's 57. So this is slightly negative, right? So you can say that, okay, if what I just find before was, if I buy HDTV, then I actually will buy an exercise machine. That was my conclusion. But here I'm almost coming up with the otherwise reason. Like, no, this is not really true. So this is a paradox. So what really is happening is, if you look at college students, they buy 10% of the time. So they have a very little buying them exercise machine is not very likely. But if you are working adult, you are buying almost 60% of the time you will buy a exercise machine, and 10% if you are a college student. So actually the real reason for you to buy a exercise machine is not because it is HDTV or not, but it is if you are working adult or a college student. So if you are a working adult, then likely you will buy a exercise machine. So if I were to actually, these numbers, if you add them up, these numbers are, if you summarize them, you are still gonna end up with 300 samples. If you sum all these up, you will, if you sum them up, you will group them and sum, and you will actually end up with this 300 number, with even these subtotals are correct. So in summary, you don't quite see that way, but in reality, what happens is actually it is the working adults in the population that actually seems to change the outcome. So had I knew that it is more likely that I will buy exercise machine, not because of HDTV, because I have more people in this set who are adult. So that actually produces a yes result, not because it is HDTV, but because I have more people in this group that are buying HDTV adults, and they are more about to buy exercise machines. So that is the underlying reason. So this is something to be careful about it. So you can't easily draw a conclusion. You may need to maybe further look down and find the real reason. So then this is another topic that's also important. When we have support distribution on associations, we may have very few items with high support, and we may have many items with low support. So here we do have a lot of items, we have low support, and we have maybe an item here, maybe it is milk, you are selling it a lot, and maybe you have a very few times that you sell maybe some special item in the store that only sells few times. So this is many real data sets have skewed support distribution, and when you are dealing with coming up with a support count, if you set it too high, we could miss item sets involving interesting rare items like caviar, vodka, for instance. But if you set up too low, then you have to do a lot of computation. You may catch, but then you will also have a lot of item sets that you generate. Then there may be a lot of rules, and that may also not mean very interesting. So how do you overcome this case when you have a situation like this? We will discuss that. But there's also another interesting thing here. So if you have cases where you have, for instance, a very high supported item and a very low supported item in the same item set. So we do have this time a cross support pattern involving items with varying degrees of support. So this is something to pay attention, cross support. And you want to avoid that. So we have a measure of cross support. This is defined by Rx. So given an item set with items, we can define a measure of cross support R for the item set as this formula, where we will find these are supports of individual items, and we want to get minimum support and maximum support, minimum of all items and maximum of all items, and then we'll get a ratio of that. And we can use then Rx to prune. Can use to prune cross support patterns, but not to avoid them. So we can actually make use of. So for instance, we have this example where we have caviar and we have milk. Milk is sold very often, right? It is really high support. So if you look at observation, we have caviar, milk. This is confidence. So meaning that given milk, what is the likelihood that, oh, okay, sorry. If I buy caviar, I will buy milk. Is very highly likely, right? Because I am already buying milk many times. So, and it may actually happen that I buy caviar and there will be already a milk in that basket. But if you look at other way around, so if you buy milk, will you have a caviar because you buy a lot of milk? That's very lowly, like unlikely, low, likely, right? So it's a low number. So for that we will need to use minimum. So confidence of caviar milk, confidence of milk caviar, and therefore we will take the minimum of that. Is also very low, right? Because it will actually use that one. So in order to avoid patterns whose items have very different support, we need to define a new evaluation measure for these, known as H confidence or all confidence. Specifically given an item set X, this is item set X, H confidence is the minimum confidence of any association rule formed from the item set X. So we have H confidence X, and we have confidence of X1 implies X2, right? These are just X1, X2. We have to do for many, like X1 is a set of X1, X2, X3, and X2 is a set of X3 and Xn. So it's something you have to do for many possible rules that can be generated from this item set. You will calculate the confidence of all of these, and you will get the minimum of that. So if you have X1 and X2 here, and this is subset of X, and the intersection is empty set, so they are not actually intersecting with at all, but their union is X altogether. So when you combine X1 and X2, it is actually forming X. So if you say, for example, X1 is X1, X2, and X2 is X3 and XD, then you need to actually look at for all these X1 and X2 and find the minimum. So edge confidence is the minimum confidence of any association rule formed from item set X. So what we will do using edge confidence, we will, to avoid patterns whose items have very different support, define an evaluation measure. We do it for avoiding these cross supports. So given an item set, again the same item set X, what's the lowest confidence rule you can obtain from X, right? So we have confidence X1 implies X2 is, we have support of X1 union X2, so together those appear, right? So we put all together, divide by the support of X1. It is like given X1, it's almost, this is at the denominator. So this, the numerator is fixed, this is fixed, so this is union and it is X Sx, that doesn't change. So what can actually change is support of X1. So how we are trying to find the minimum, if you remember. So for that we need to find the highest of all for that. So consider only rules where X1 is a single item, then we will have the highest, right? As you go down, it will actually have a lower support, and so when they are just by themselves, you will likely to see them more often. So edge confidence, you need to get the minimum of these. So I'm looking at this, this and that, right? Minimum. And we know that this is fixed at the top, so I can actually get the maximum of support of all these items. So actually finding the item with the maximum number, I can use that as that edge conf number. So this is fixed, and this is, by using the maximum of that, I can actually calculate that edge confidence. By the anti-monotone property of support, so this is minimum of this is greater than Sx. Therefore, we can derive a relationship between the edge confidence and cross support of an item set. So this is edge confidence. If you remember, this is the formula. We just gave this formula right there. And we also have support of X is less than equal to, right, support of, sorry, minimum of any of these. So this will, if you have a number here, then it will be, this will be greater than Sx. Therefore we can actually now, this is our, this is edge conf number, remember here, this is, where is R not, okay, this is our Rx, and this looks like the bottom part, right? So now if you bring them together, you can actually establish a relationship between hconf and Rx. Thus we can actually state that fconf x is less than Rx. So why is this important? Since hconf is less than Rx, we can eliminate cross support patterns by finding patterns with high confidence HC, a user set threshold. So we can basically say that we will set some HC, a threshold value, by ourselves, with knowing that relationship, which is less than 1, and this is hconf is less than Rx. And I can actually set a edge confidence threshold value and use that to eliminate lots of items or rules in the pattern. So I'm finding patterns, I can eliminate that. We can eliminate cross support patterns, by finding patterns with edge confidence less than this. Any item set satisfying a high edge confidence threshold is called hyperclique. If it satisfies a given edge confidence threshold, edge called hyperclique, and edge confidence can be used instead of or in conjunction with support. We can either use that one or confidence, support, or this one, or together we can use that. So hypercliques are item sets, but not necessarily frequent item sets, good for finding low support patterns. Edge confidence is anti-monotone. We state that can define closed or maximal hypercliques like closed and maximal frequent item sets. We can also do the same thing for hypercliques. So what is it used for? So hypercliques have the high affinity property, meaning that think of individual items as sparse binary vectors. Edge confidence gives us information about their pairwise Jacquard and cosine similarity. So you can actually look at the relationship between Jacquard and edge confidence. Hypercliques that have a high edge confidence consist of very similar items are measured by Jacquard and cosine, as measured by Jacquard and cosine. The items in the hyperclique cannot have widely different support. So we are actually pruning those. So they are not too, by setting a HC threshold, if I have an item which is very high in the frequency and very low in the frequency, and looking at that, I can actually eliminate those item sets, and then basically patterns that are associated will be eliminated, so I can actually do a more efficient pruning. Basically what, just to summarize, because I know this is a lot of stuff, heavy concepts here, but basically what we have been trying to do is come up with a way to eliminate rules that will actually mess up our rule generation. So we have, because situations where we have cross support patterns, like here caviar and milk example, just because caviar happened to happen with milk, it doesn't mean that it is actually real, because milk has already been there so many times, right? So it is lifting it, basically milk is lifting the caviar's probability as if it is interesting, but it really does not look like. So we can use those patterns that are actually not really interesting because they happen to be supported by the other item in the item set. So this is the purpose here. So again, we are actually using some techniques to improve our rule generation. Example of a hypercliques. It is used to find strongly coherent groups of items, words that occur together in a document. Like this is an example: biological process, physical process, metabolism, catabolism. So these are some p-values here. So these happen to have very low p-values, and they seem to be more likely together appearing. Proteins in a protein interaction network. In the figure at the right, a gene ontology. For instance, this is another use, proteins in a protein interaction network, because we have a lot of proteins, a lot of interactions among them, and we may have very few proteins that we are looking at in a, like looking a needle in a haystack sort of situation. You don't want to miss that if possible, so you may actually focus on that. In the figure at the right, a gene ontology hierarchy for biological process shows that the identified proteins in the hyperclique perform the same function and are involved in the same biological process, so you don't miss that. These are, we have item sets, then we also have, as if it is, we have hypercliques. Think of the individual items as sparse binary vectors. we can are item sets, but necessarily frequent item sets. So we have low support patterns that we are looking for. But when we are looking for these low support patterns, we don't want to get lost in this big mess when we have like items where they are really a lot, and it is actually when you put in the numbers, it actually diminishes. I think this is enough for rule evaluation, and I hope it will help. Definitely I can understand the last parts will be a little bit difficult in concept. Unless you really use it, you will probably see the need for it, then you appreciate it. But in general, if I just were to summarize it, we have a number of measures and they have different properties to remember. Among those, you need to be really watching lift, right? Lift is important for us, and lift is like, I think this is something you can you can also think about it. Just because it is coffee, it is already having 0.9 support, you actually talking about a 0.7 support, it does not mean anything. It is not even positively correlated. We know that it is actually negatively correlated. If you don't drink tea, you are more likely to drink coffee, which makes sense, right? But if you just use confidence, that can actually mislead. So this is something to take as a lesson. When we have a statistical dependence, these are the measures we can use. And we could also have statistical independence. So then these are really not related. Like one doesn't indicate the other, for instance. Those are just independent events. It's not associated, basically, right? And this is contingency table. You will probably see this a lot. And one more thing, I think I should probably just iterate. So we have different properties of these like variable permutation property, scaling property, property under inversion operation. Phi coefficient is an example where we actually show you that it actually does not. We have null addition, adding irrelevant items to that list. So we have different properties and a summary of that, how these measures does that. Support, we talked about that. Phi coefficient is, so you may need to decide where you will use it. We also have Simpson's paradox. I just couldn't say it, but this is important. Hidden variables may cause the observed relationship to disappear or reverse its direction. So here we wrongly concluded that HTTV is the driving factor, but if we look at it underlying, it isn't. It's actually even negatively affecting it. It is just because I have another variable that I didn't look at it. It's about adults, working adults or a college student, that actually drives if you will buy an exercise machine and not. So don't get lost. So this is also an important lesson, like that you have to be careful. We also talk about situation when we mix very high and very low. We have a situation where we may miss certain things. So we have mechanisms to actually focus on those. And I think this is enough. So far so good, and I think this is done for data mining in general. This is the last chapter. Okay, that's it. See you.